Come on. All right, let's get started. So there's 2 seats up here, and then there's a couple more that are that just have like a jacket or something, and then one more empty one over here too. So yeah, so one thing is I posted on Piazza, the department said that I can't have people standing in the aisles, and that's generally true, but it violates the fire code. So if you're in the ad section or not registered, you need to make sure that there's enough seats for the people that are registered, and then if there's enough seats for you, then you can see the class in person. Otherwise, you'd have to use the video. The ad section is technically a video-only section. One more thing is, so I just sent the wait list last night to the academic offices. There's a few seats. I think there's enough seats for you guys. So students should be added to that pretty soon. I guess probably many of you, if you haven't already, if you're not already registered or want to know where you are in the wait list, if you could just wait a couple days until that gets, until the wait list gets moved, part of it gets moved to the ad list, then that will take care of most of you. So I don't want to answer 90 questions about what order am I. Just wait a few days, and then if you're not already there, I can let you know how close you are to the top, so that you can see if there's a chance, what the likelihood is that you'll be able to be added after people drop. I created 50 more seats, so it's more than I originally planned. And I think that's about as much as the course can possibly support without having to change the structure. Okay, so today we're going to do a review of lighting, brief review, and we're going to mainly talk about image filtering, so what it is and how we do it, and I'll talk about color models as well. So to review, albedo is the fraction of light that's reflected. And it also determines the brightness and color of a material. And so, for example, this is like a cloth bag. The outside of the bag has very low albedo, and the inside of the bag, which has a white lining, has a higher albedo. More light is reflected from the inside. Question?
Yeah, how does a mirror work in terms of albedo? Because technically it doesn't absorb any light, right?
Yes, that's a good question. So the question is, how does a mirror work in terms of albedo? I think the albedo would only be, the albedo is defined as the percent of light that's absorbed. Actually, mirrors don't usually have perfect reflectivity. So even something that looks like a pretty good mirror might be reflecting 70 or 80% of the light. So it may still have some albedo. But so I guess so in total the definite, or not in total, but if we just stick to stick to specular reflection, Lambertian reflection, and albedo, then albedo is the percent of light that's absorbed by the material at different wavelengths, and even for mirrors there will typically be a non-zero percent. And then Lambertian is then you might say that some percent of the surface is some percent Lambertian, meaning that to some extent it will scatter the light, and some percent specular. So for like a glossy wood surface, it might be like 3% specular, 97% Lambertian, and then it's absorbing maybe, I have no idea what percent, but some percent of the light that it's receiving in different wavelengths. Question?
If different materials have the exact same albedo at all wavelengths, would it be the same color?
Yes. if two materials are Lambertian at least, and then they have the same albedo across the spectrum, then they would, in the same lighting, they would have the same color. Yep. So sorry, I have to repeat the question. So the question was, if two materials have the same albedo, would they have the same color? And the answer is, yes, if they're Lambertian. If they're specular, then they'll be reflecting other things around them. So specular means that the light bounces off of it like a mirror. So what you see depends on your viewing angle. And the reflection color is the same as the incoming light color. And diffuse reflection means that the light scatters in all directions. And so the amount of light that's received by the surface depends on the angle with respect to the light source. And then some fraction will be absorbed, some fraction will be scattered. And the amount of light that you observe does not depend on your viewing direction. So like with the chair backs or the wall, if you move your head around, it doesn't really change the color of the wall, except at like some places, maybe, well, actually, that's for me. Some places where you're observing the reflection of the light source. Yeah, so the reflection color does depend on the light and color and on the albedo. So, so this is just saying again that the amount of light that hits a surface from a distant point, or from any illumination really, depends on the angle between the surface normal and the source. And just to restate, this is a dot product between a vector that tells you the direction of the light source times the intensity of the light source, just modeling intensity as a scalar instead of depending on wavelength. And this is the normal vector of the surface. If you take the dot product of two normalized vectors, that's the same as the cosine between the vectors. So this is equivalent to saying rho of x times cosine of the angle between these two directions times the intensity of the source. So, so to summarize, Lambertian, it's all diffuse, light scatters, specular, reflection like a mirror, and then glossy is some mix of them. So we can answer questions like, if we have some mix of specular and diffuse reflection, we can often answer questions like, how many light sources are in the scene, and I can estimate the color of the camera's flash. So first, how many light sources are obvious in this scene? Two, yeah. So a lot of people are saying two. So that seems good. There might be more, but you can see like that there's at least two. There's one that's reflecting on the top of the balls. That might be like up here. And then there's one that's the flash of the camera probably because it's reflecting back at the camera roughly. So then, does anybody have an idea how I would estimate the color of the flash, given that I have, if I assume that this is like mostly diffuse, but there's some specularity, and the specular component that I actually observe will be, like these little specularities will be reflecting the light of the flash. How do I estimate the color of the flash? Yes?
Specularities should have the same color then, right? Because it's reflected right.
Yes, so the specularities should have the same color as each other. But how do I estimate the color? Because it's the complication is that underneath that specularity, there's still the diffuse reflection. So the specularity, I guess if you think of just the specular component, that should be the same color in these different surfaces. But there'll be a yellow component from the cue ball here and a green component from the cue ball there. Yes?
So if I just subtract the color of the whole ball from what we see in the specular.
Right, yeah, the answer was subtract the color of the ball that we see that's outside of the specularity from the color that we see inside the specularity. So I'm going to plot that. Let me see. So I've got some, I'll have to move my MATLAB over probably. Okay. Let me get one of my figures. It's showing up on the wrong screen. Okay. So I'm plotting this line that goes right through the specularities on each of the balls. And now, let me grab the other figure. Okay, so here you can see the plot. So here what you're seeing is actually the change in intensity that's due to the curvature of the ball. So the flash is illuminating it head-on most, so you can see it's very dark on the outside, and then it's getting brighter and brighter and brighter. And here's the specularity. So then again, it goes off, it hits the edge of the yellow ball, and it hits the green ball. So green starts, well, it's pretty dark green, but green goes up a bit. Now here, this little bump is where it's on the white part of the green ball. Then it has a sudden drop where it hits like the dark part. And then it has a sudden spike where it hits the specularity, and then it drops, and then it goes up again where it hits the white part of the 14, and so on. Okay, so one thing that's a little bit tricky is if I do exactly what was suggested, then I run into saturation. So at this point, I've got 244, a specularity, the intensity is 244, and I also have undersaturation in the blue channel. So here it's like 0, so it's hard to say exactly what the blue intensity was since the values will be very compressed in that range. Also, if I look at the specularity on the green ball, it spikes up to 255, so the actual value isn't very helpful. But what I can do that's very similar is I can take the difference between 11 and 12, 111 and 112, which are just, so the specularity, in fact, is not going to be like a single solid ball. It will be more diffuse towards the outside and then get brighter as you go towards the center. And so if I look at the difference of intensity between 111 and 112, that's entirely due to the specularity. In that 1 pixel, there's not going to be much change due to the curvature. But there's a big change because I'm like getting right into the center of the specularity. So I can do that in each of the, I can look at these differences in each of the color channels, which I did ahead of time so that I don't have to type it out. And so this is the RGB channel at x equals 112. This is the RGB channel at x equals 111. So I take the difference. And then if I, got like 9 reconnection attempts left. And then if I, so let's say, all right, so then I can just normalize that to, let's see, answer equals answer divided by sum. It's really hard to type when my back is turned. Answer equals answer divided by sum answer. Okay, so then I can do figure 3. Okay, so now I'm just going to create an image that has these relative intensities, and then I normalize it so that the brightest of them is 1. Now I have to drag that figure over. So you can see that based on that estimate from that 1 specularity, the color is kind of like a slightly yellowish color. And then if you wanted to, be more precise, you would probably want to look at all the specularities of all the balls, and then you could get a better estimate.
So basically, you looked at points 211 and 212 and compare the differences.
Right.
So
Yep.
you're comparing the diffuse aspect of the specularity.
Well, so the idea is that the diffuse part will be constant between 111 and 112. The diffuse reflection like if there were no specularity, basically there'd be very little difference in intensities. And the difference is because the specularity is like hazier on the outside than on the inside, so the intensity of the specularity is increasing as I go inwards. And so most of the difference that I observe is due to that, that change in the specularity intensity.
And what about the normalization? What was that answer?
So I was just normalizing it so that I could say like what percent of the intensity is due to the red, green, and blue channel. I still wouldn't necessarily, it's still hard to estimate the overall strength of the reflectance of the specularity compared to Lambertian because it's saturating in the center. So I was just doing like the relative colors of the lights. A couple more questions. So there, and there. So start here.
Could you please go back to the signals?
Yeah, sure.
So right before the peaking the specular region, there is a drop in the signal. So what is that? Would that be 111 or the red one?
Yeah. So the question is, why is there a drop right before this? And it's just because there's a little dark spot from the stripe of the green ball. So it gets into the dark spot, then it quickly hits the specularity, and then it gets into the dark spot, and then it hits the white spot. So here's where it starts to drop from hitting the dark spot, and then it hits the specularity, then it hits this like dark area again, and then it hits the white spot. So that's what it is. It's a change in color from white to green. There's a question back here too. So the question is, will the saturation cause distortion of the rest of the image, right? No, it should only affect the pixel that's saturated. So the CCD should be measuring the light independently. There is, I guess, under a perfect imaging system, like every cell would correspond to a specific range of orientations. Imaging systems aren't perfect, so there's usually some amount of blur due to the lens. And so I guess to that extent, if you had really strong light coming in at some particular angle, it could affect the surrounding pixels because there's a small amount of blur due to the camera, physics of the camera. But otherwise, the amount of light that comes into one CCD cell should not affect the saturation of the other cells. Question?
How did you draw that line?
So the question is, how did I draw the line? And where's my mouse?
Did you draw it manually?
Yeah, well, yes. I mean, I copy and pasted commands that I'd saved, so I did plot. Yeah. Manually, as in with my keyboard, yeah. Yeah, it's just a line plot on top of the image. And then I did subplots for the other figures. So this code is actually in the slides under notes, in the notes of the slides. Oh, question back there?
Just to confirm, the reason why you chose that particular point for getting the color of the flash was because the intensity difference was coherent for all the three different graphs, right?
Right, yeah, so the question is, why did I choose that particular specularity? It was because it wasn't saturating as much as the other ones, but there was still like some non-zero intensity of the other channels before the specularity. Okay, yeah, sure, one more question on this.
We're doing like the picture where there's like local differences and it's basically lines and it kind of took out the colors. There's circles around this specularity.
Sorry, what was the question? Were there circles?
Would there be a circle around the specularity because there are differences, local differences between the pixel brightnesses?
Do you mean our specularity is circular?
Sort of, but there was like this one image that we're looking at with like the lion and the zebra on the cycle, and it's basically plotting the local differences of the brightness, right? do that to something like this, would we see that the specularities would be singled out?
Oh, yeah. So the question is, like, if we were to do some kind of like edge processing or difference processing, would we see circles around these specularities? And yes, in this case. So there are some specularity detection can be kind of difficult, though, because it can be hard to tell the difference between like a change in albedo. So this getting brighter just because the surface changed versus change due to illumination. But if you look at like sudden like bright spots that become saturated, those are likely due to specularities. If there's like small spots where it gets suddenly brighter and it gets saturated. So if you were to do like an edge image of this, you would see like little circle edges that are little circles around these specularities, lighter here, as well as like, you know, around the white parts of the center of the ball. Okay, so so the importance is in the important part of the signal is really in changes. Even when I'm measuring like trying to measure the color of the light source, I'm looking at the changes of intensity rather than the absolute intensities. And that's because there's an assumption that for nearby scene points, most of the factors don't change very much. So if we look at the local differences, then that tells us about some kind of change. So this is so here like the dark pixels are large differences. Here dark pixels have a large difference. So you can see the edge of the shadows, you can see like some texture on the walls, the lines of the wooden structure, the lines of the sign and of the telephone wires and so on. And that contains most of the information for shape. We can still interpret that image. So today and in the next two classes, we'll talk about image filters in the spatial domain, where filtering is first today, where filtering is a mathematical operation on the values of each patch. So we can do like smoothing and sharpening and measuring texture. On Thursday, we'll talk about filtering in the frequency domain, where we think about it instead as a way to modify the frequencies of an image. So for denoising, sampling, image compression, for example. And then the following Tuesday, we'll talk about templates and image pyramids, where we used filtering as a way to match a template to the image. So we can do like detection and course-defined registration. So remember that the image is really just a matrix of numbers. That's the raster image. A raster image is just a grid of values. And so what we want is to build up tools that let us analyze that image or extract useful information from it. So take a matrix of numbers and then actually infer something about the scene or something about the thing that's being imaged. So image filtering means that for every pixel, we compute some function of a local neighborhood and output a new value. And the same function is applied to every position. And the output and input image are typically the same size. So it could be as simple as a smoothing filter, which we'll talk about today, or as complicated as an object detector that's trying to produce a likelihood that there's an object at every position. So now we're going to talk about linear filtering, where that function that operates on local neighborhoods in the image is a weighted sum or difference of pixel values. This is a very important class of filters. So this can be used to enhance images, doing denoising, smoothing, increasing contrast. We can extract information from images about texture, edges, distinctive points. And we can detect patterns using template matching, all with linear filters. So here's a simple example. It's a box filter, because if you were to plot implicitly anything that's not defined here is like zeros everywhere else. And if you were to plot this, you would see a box with a height of 1 in the center, and then zeros everywhere else. So it's a box filter. And the 1/9 is just normalizing it so that when I apply it, then the average intensity of the image won't change. So for filtering, you slide this filter over every position in the image. Later, I'll talk about what happens at the border cases, but let's just not deal with that for now. So I slide it over every position in the image, and I multiply the values in the image. Here it's a 3x3 array of zeros with my filter, which in this case is a 3x3 array of 1/9. and I take the sum of those values. So it's basically the dot product of this vector with the dot product with, the dot product of this vector with this vector. So 0 times 1/9, 9 times added up is equal to 0. Then I take a step to the right, and now it will be 0 times 1/9 plus 0 times 1/9 plus 0 times 1/9, etc., plus 90 times 1/9 equals 10. Take another step to the right, and now I've got 2 10s, so it'll be a total of 20, and so on. Right? So I do that for every single position in the image. I do the sum of every element inside of this local window with every corresponding element in the filter. So what's the value at this position where the red box is now? Yes? 50, right, because it's going to be 90 times 1/9, these 5 times, plus 0 times 1/9, these 4 times. And the total is 50. Okay, and here? 90, right, because it will be 90 times 1/9, 9 times, which is 90. And so this is the whole image. So what does this box filter do? There's a couple of different ways of describing it, but what's one way to describe what the box filter does? Yes? It does 2D convolution, but actually any linear filter is doing 2D convolution. So I mean specifically in the case of the box filter, what is the box part doing? Yes? Yeah, so that's one way of describing it. So it creates some kind of smoothing effect. If you look back at this, this was very sharp. This has more of a gradient to it. What kind of mathematical operation is it doing on local neighborhoods? Averaging, right. So it's also computing, it's replacing every pixel with the average of its neighborhood. So one thing I didn't make super clear was that you always replace the center. The output image will be, you replace the center of this local window with the function that's computed over the window. And if you have so typically you want to have an odd number of elements in your filter, so that's well defined if you care about that. Otherwise it will just, be, you just have to have some definition of it goes to the left or to the right if you have an even number. So here's smoothing of a big box filter on this straw texture image, and you can see that it does create some smoothing effect. So let's look at some other filters. So what will this filter do? Right, so people are saying nothing. This won't do anything because what it will do is just it'll replace every pixel with itself. There are no non-zero values outside of the center, so it'll just be the center minus, replace the center with itself, no change. So that's the identity filter. What will this one do? This one's a little bit trickier. Yes, so it will shift to the left, right? So the left versus right is a little bit tricky. It's to the left because every pixel will be replaced by every pixel will be replaced by its neighbor on the right. So everybody moves to their left one space. What do you think this will do? So we can do linear combinations of filters, as I'll get into a little bit more later. So if I do, so this is a double identity, 2 times. So this will, you could think of it as I'm doing twice the original, but then I'm subtracting the average of the local neighborhood. So, so what will this do? I think you had your hand up first.
Invert the intensity?
It'll what?
Invert the colors?
No, it won't actually invert the colors because it's still going to be the total sum is still positive. So back there. Yes, yeah, so it's doing the opposite, right, it's sharpening. So it will, you can think of it as that you take the image, so that would be like an identity, and then you add to that another identity minus the average, which will be strong if the average is different than the center, and it will be weak if the average is the same as the center. So when you add that to the original image, then you get some sharpening effect. So here you can see it on the whole image. Even on the projector, you can see that the lines of the suit are much sharper, and the lines on the tie and on the face, it's much sharper after the filtering than it was before. So it's accentuating the differences, local differences. So here's some more filters. This one's a vertical edge detector. It's a Sobel filter. So here I took the absolute value of it. Otherwise, you'd get strong negative or strong positive values, depending on which side is black. I mean, which side is darker. So you can see like that there's vertical edges, like the edges of the suit light up where it goes from white to black, white to gray or gray to white. Also the edges of the eyes where the white part hits the iris. And then this is the horizontal edge filter. So, so this lights up like at the part with the lapels hit the tie and so on.
What's the difference between, why would you want to use one or the other?
Well, one of them detects when there's edges of a vertical orientation, and the other one detects edges of a horizontal. So they'll often be used in combination. Usually what you want, most often you want the total edge strength. So you would have some kind of horizontal and vertical edge detector, or edge detectors at different orientations. And then you'll use their relative strengths to find the angle of the edge. So the simplest edge detector you could make would be a horizontal gradient detector, which just does the difference to left and right, and a vertical gradient detector. And then you can calculate the angle. We'll get into this more in another class, but you can calculate the angle as the arctangent between, or ATAN2, between the vertical gradient and the horizontal gradient response. And you can compute the magnitude as the root of some squared values of the response. So that way you get the strength of the edge and the orientation of the edge. This is the same. Your filters don't have to be square. It's always assumed that the center of the filter that you define is the center of the filter that's being operated, and that anything that you don't define is a zero. So you can think of this, since this is all zeros, you don't really need it in there. Okay, so here are some ones to think about. I'll give you like a minute or so for each one. So let's do the first one first. So the task here is to try to write these as filtering operations plus some element-wise operations. So for example, if you wanted to like double the strength of an image, one way to do it would be to filter with identity and then multiply the image by 2. Obviously, filtering with identity isn't necessary, but it's just an example. So here, the first one is, what if you want to compute the sum of the 4 adjacent neighbors plus 1? So for every position, mn, I want the response to be 1 plus the sum of the 4 adjacent neighbors. So I'm doing a sum over these two variables, which are -1 and 1, so that I do like m minus 1, n minus 1, m minus 1, and plus 1, and so on. So think about it. I'll give you a little bit of time and see if you can come up with the solution. so how many people have got the solution to the top one, to number 1? Okay, a few people. I'll give you a little bit more time. Okay, let's do the solution now. So how many people have got it? Or think you have it? Raise your hand. Okay, not a lot of people yet. But let's do this one because doing one might make the other ones easier. So, so who wants to volunteer an answer? You want to go ahead?
So it's the filter 0, 1, 0, 1, 0, 1, 0, 1, 0, and then we have 1.
Yeah, I'll assume. So, okay, so you can say that the filter is that. Okay. Wow, that really isn't. Let's try that. Okay. Stop. Yeah. And let me try. Let's try. All right, so let me just try turning it off and on and see if it will stop freaking out. So, yeah, so I make a filter that's 1, 1, 1, 1, and 0 everywhere else. So let's draw that. 0, 1, 0, 1, 0, 1, 0, 1, 0. And then if I do out equals, this is using, oh, I probably, okay, it's there. If I do out using IMFilter in filter plus 1, so I don't know how to make it stop doing that. Then it will, so this will sum the 4 adjacent neighbors, and then it will add 1 to the final result. Okay, so that's what we wanted. Okay, so second one. This one is a little trickier, but now that you've seen one, maybe it kind of, the pattern will start to emerge. So I want to sum the squared values of the 3 by 3 windows around each pixel. Note that sum is not a linear, sum is. Squared is not a linear operation, but I'm allowed to do element-wise stuff to my matrix as well. Yes?
Do you change the matrix by first multiplying element-wise with itself and then playing with the
Yeah, so I can do element-wise operations to the matrix. I just want to give, in case not everyone heard it, I want to give them, that's right, but I just want to give a little bit more time for people to think about it. Yes? Putting what? Uh-huh. By the curly brackets, I mean that it's a set rather than inclusive than the range. So it's only K and L only take values of -1 and 1, not 0. So that's why it's only going to be the corners. Yeah, so they could, oh, yeah, you're right. Yeah, so I should have written that differently.
But you meant in the first question only outlet.
Yeah.
This one is all of them.
Yeah, you're right. Yeah, I wrote that wrong under the sum. So I'll fix that another time. So for this one, I think this one works. So for number 2, okay. So the answer that was given, which was correct, is that you can square in first element-wise, and then how do I compute the sums? Right, so if I have a filter that's all ones without the normalization, then that will be the sum. So it would be, for number 2, out equals IM filter in point times in ones 3, 3. Okay, so this will be the sum of squared values in a 3 by 3 neighborhood around each pixel. Ones 3, 3 creates a 3 by 3 matrix of ones. So the third one is that I want to know if the center pixel value is larger than the average of the pixel values to the left and right. Just give a little bit more time. Okay, I think, did you have the answer back there? Sorry, what was that?
Can use the sign operator over the -half, 1, half.
-1, sorry.
-half.
Yeah.
Minus half.
Right, so we can just use that filter, and then how do we get and then we want the result to be 1 if the center is greater than its neighbors, and 0 if it's less than. So if I just use that filter, that will still give me some continuous values.
Yeah, I meant to use the sign operator.
Oh, sign operator. Okay, I understand now. Sorry, I thought you were saying sum operator. So yes, so let me just write it out. So we can do a filter that's a simple filter that's -1/2, 1, 1/2, -1/2, right? And then out equals IM filter in fill greater than 0. So if the center value is greater than the average of its neighbors, then this is going to be positive. then the filter response will be positive. If the center value is less than the average of its neighbors, left and right neighbors, then the response from IMFilter will be negative. And so when I threshold it, then I'll just get a response of 1 or 0, depending on whether it's greater than or less than its neighbors. All right, so it was mentioned earlier that filtering and there's some equivalence between filtering and convolution. So just so you know, in MATLAB, if you do filter 2 and IMFilter, they're basically the same, but filter 2 requires a particular ordering of the filter and the image. So in filter 2, they define it as that the filter is first and then the image, where in IMFilter, typically the image is first and then the filter. Although mathematically, there's not a difference between filtering an image with a filter and filtering a filter with an image. They're both images. Convolution, 2D convolution has an equivalence to linear filtering, but convolution is usually defined as that instead of where in filtering you can think of it as like you line up the filter with the image and you take the dot product. In convolution, instead of it being like if you're doing a sum over the elements of the filter KL, instead of it being m plus k and n plus L, it's m minus k and n minus L. And so that's just has the effect of rotating the filter. So convolution, if you do conv2, if your filter is symmetric in the right way, then you'll get exactly the same response, but otherwise it will be like you rotated your filter, I think, 180 degrees. So usually we just use IMFilter in this class, but there's, and under the hood, they'll all be doing the same thing if you're doing linear filtering. So some key properties of linear filters. So one is that they're linear. So if you take if you filter something with F1 plus F2, that's the same as filtering it with F1 and then filtering it and then adding that response to the filter with F2. There's shift invariance, so the same filter, the filter operates the same everywhere. And if you were to translate the image and then apply a filter, then you'll get the same response as if you apply the filter and then translate the image. And any linear shift invariant operator can be represented as a convolution. So some more properties. It's commutative. So filtering A with B is the same as filtering B with A. Associative. So if you filter B with C and then filter A with that result, that's the same as filtering A with B and then filtering that result with C. So as an example, if you had like 2 smoothing filters, you could apply one smoothing filter to the other smoothing filter and then apply that result to your image to smooth it. Or you could apply those 2 smoothing filters successively to your image. And either way, you'd get the same output. Distributes over addition. So if I filter A with B plus C, that's the same as filtering A with B and then adding the response to filtering A with C. And then similarly, scalars factor out. So if I filter K times A with B, that's the same as filtering A with B and then multiplying that by K. Or if I filter A with K times B, that's the same as filtering A with B and then multiplying by K. Where multiplication there, I mean element-wise, not a matrix multiplication. And then the identity is the unit impulse. So it's just a field of zeros with a 1 in the center. And that does nothing to the original signal. The output is the same as the input. So this is one important filter, a Gaussian. This is the main filter that would be used for smoothing. And I'm showing various representations of it. So here's like a 3D plot of the Gaussian. Here's an intensity image of a big Gaussian. Here are the numbers for a small Gaussian. You can get this, and if you're using MATLAB, you can use F special to create a Gaussian. or you could even create it from the formula. So this is the formula for a Gaussian. So a Gaussian is a good smoothing operator. You can see that it creates this nice smooth image from the straw image. And it's actually, even though averaging might seem like the ultimate smoother, if you compare the box filter to the Gaussian, the box filter actually is kind of edgy. You can see like some sharper edges on the outsides here, where those go away with the Gaussian filter. So the box filter is actually not a very good smoother. And to understand that, we need to get into frequencies, which is what we're going to do in the next class. So a little bit more about the Gaussian. The Gaussian removes high-frequency components from the image, so it's called a low-pass filter because it lets the low frequencies through. And the perceptual result is that the images become more smooth. If you convolve a Gaussian with a Gaussian, you get another Gaussian. So the advantage of that is, or one thing that can be helpful with knowing that is that you can make a big smoother by doing a lot of small smoothing operations. So if you're doing, sometimes with the GPU processing, it's faster to run. You need the filters to be of a smaller size to be able to process efficiently. So if you want to do a big smoothing operation, it might be more efficient to run a whole series of 3x3 or 5x5 smoothers rather than running one big like 50x50 smoother. And the Gaussian is separable, which means that you can factor it into the product of two 1D Gaussians. So mathematically, what that means is that if you can see it from the function, that I can take this 2D function. So this is 1 over 2 pi sigma squared times e to the negative blah, blah. You can read it. And then I can separate that out into a function that depends only on x and a function that depends only on y. So I can express the 2D Gaussian as a product of two one-dimensional functions, one a function of x and one a function of y. And in this case, each of those functions are 1D Gaussians. So we can use that in filtering. So instead of having to filter, if I have a separable filter, this isn't quite a Gaussian, it's more of a triangular filter. But if I have a separable filter like this one, then I can break it out into a vertical component and a horizontal component. Note that if I filtered this on the right side with this on the left side, then I would get this as my output. So I can perform the same filtering operation by first filtering along the rows and then filtering along the column. And then I'll get the same output in the center. Here I'm just showing the output for the center. So why is this useful? Why would I care about a filter being separable? What's the advantage? Yes? Yes, the answer is that computationally it's much cheaper. So it's not so noticeable with a 3x3. But if you think about it, the total, the time to process this way with spatial filtering is the number of elements in the filter times the number of pixels in the image. And if I've got, say, a 25 by 25 filter, if I can break it up into a 25 by 1 and a 1 by 25 filter, then my computational time is 50 on the order of 50 times, so 25 plus 25 times the number of pixels. Where if I keep it in the original 25 by 25, then it's on the order of 625 times, which is 25 times 25, 625 times the number of pixels. So, so especially for larger filters, if you have a filter that's separable, it's much more efficient to separate out the 1D filters and then filter sequentially. Okay, so let's get to some other details that are important for implementation. So one question is, how big should the filter be? In some cases, like with a box filter, then it's just the size of the region that you want to average, and everything else is 0 around it. But for some signals, like a Gaussian, it has an infinite domain. It never goes to 0 exactly. And so you just have to cut it off somewhere. So anywhere that's not defined is going to be assumed to be 0. So you're always creating an approximation of the true Gaussian function with your filter, because the full Gaussian would be an infinitely large filter. But it does go like pretty close to 0. So the rule of thumb is to make the half width of the filter to be 3 sigma. So for example, with sigma equals 1, you would have a 7 by 7 filter, which would be from about here, number 7 on this line, to number 13 on this line. And for a sigma 3 filter, the size would be would be 19 by 19. Sorry, I mean it would be 19 by 19. So you'd have 9 on each side plus 1 in the center. So if you have a higher standard deviation, if your filter sigma is the standard deviation of your Gaussian, if you have a higher sigma or a wider Gaussian, then you need a bigger filter to accommodate it. If you choose, this is pretty important, if you choose a filter size that's too small, then you'll be effectively creating like a box filter. So if I have sigma equals 3, but I only make the filter go from like 8 to 12 here, then I'm cutting it off right there. So I basically get like a little hump, but then it just drops to 0, and it's more like a box filter than it is a Gaussian filter. So another thing that I put off until this slide was dealing with the edge of the image. So if you want to compute the filter response at the corner pixel, then the problem is that your filter will fall off the edge of the image. And so the question is, like, what values do you compute when you're outside of the image? And there's some different ways to do this. So one is that you do it's called a clip filter. So it just means that you assume that there's zeros outside of the image. And so you pad the image with zeros. You run your filter, in this case a big smoothing filter. And then you crop back to the original size. And so this is a really simple, often default way to handle the edges. But one downside is that you get like this black border here. So if you're doing like a huge smoothing and you care about the edges, then that won't give you the ideal looking image at the end. Another one is wrapping around, and I think this would make sense if your image is not like a normal, like if you're not actually taking an image of a like normal scene, but it's of some like map or something that's actually a projection of a sphere or something onto your image. But this one just does, this is something that's available in MATLAB, but you basically copy the bottom onto the top and the top onto the bottom in left and right, and then smooth, and then clip. Crop. Another one which makes more sense for most applications is copying the edge. It's also very efficient. That way you get, on the upside, you're copying like similar colors over here. So when I smooth it and crop it, it doesn't create any noticeable artifacts, because you can think of this as like kind of trying to guess what would be on the outside. The one downside of this is that if you're running a detector or something like that that's looking for edge information, this creates these horizontal and vertical edges, which might create a misleading score from the detector. And then another one is reflect across the edge, which is another good way, another like reasonable approach to try to simulate what would be outside of the image. So this kind of preserves the overall frequency statistics. I mean, like where you have horizontal and vertical edges inside the image, and it looks fine when you smooth it and crop it. Question back there?
So would you typically just like copy like one single pixel on the edge, or would you do what you're doing, like kind of chunk it?
So you have to. One thing is that you don't usually have to do this yourself. Almost any image processing library will do the padding for you, but it's necessary to pad to at least the half width of the filter. Because if you have like a 5 by 5 filter, then you'll have 2 by 2 pixels, you'll have 2 pixels hanging off, potentially on each side. So you need to add a border of 2 all around the image. So if you're in MATLAB, you can do this just with IMFilter. This one, IMFilter FG0, where F is the image, G is the filter, usually. 0 just means you pad with zeros. You could put another number to pad with another number. This does the wraparound. This does copying the edge, replicate, and symmetric reflects across the edge. Sometimes you might want to just do like the clip filter just because it's faster. If you don't care if you don't really care about what happens on the edge of the image, or you're using a small filter. So the other thing is, what size do you output? So you've got 3 options. So one is that you could produce a response anywhere where the filter at least touches the image. So that would be full. You could produce an output that's the same size as the input image, which is typical. And that means that you'll discard anything where the center of the filter is outside of the image. Or you could do valid, which says, like, I don't really want to extrapolate the borders at all. And so I just want to produce responses where the entire filter is within the image. That will result in shrinking the output compared to the input. So again, if you're using MATLAB with filter 2, then you can specify these. If you use like IMFilter, then it will just do same, which is usually what you want to do. Okay, so in the remaining like 10 or so minutes, we're going to talk a little bit more about color and about color spaces. So remember that when we process, the way that a color camera works is that you've got a CMOS sensor that's receptive to all light, but then you put a filter on it. Usually, like a Bayer filter is a classic example that filters out all the light except for light of some range of wavelengths. And notice that you don't have red, green, and blue everywhere. So actually, each cell only senses green, blue, or green, or red. And there's more green than there is blue and red. And so actually, when you create an RGB image, you're interpolating the values of red, green, and blue across the image. So, so you have to fill in all these blue values by, as a simple approach, taking the average of the neighboring blue values. And same with the green and the red. And then you get a dense map of red, green, and blue values, and that's the image that's saved. So the RGB image is these 3 color channels, 3 matrices. And in MATLAB, that will be represented, or anywhere else, basically, it'll be represented as a matrix. But there's a couple things that are worth pointing out about MATLAB representations if you're not used to doing image processing with MATLAB. So an image is just a matrix like any other matrix, and so it's really thought of as rows and columns. So the upper left, this is 1, 1. This is the first row in the first column. Also, MATLAB starts counting with 1, where a lot of languages start counting with 0. So 1, 1, 1 is the top left pixel value in the red channel. YXB is Y pixels down, X pixels to the right, and in the bth channel. If the image is n by m, then NM3 will be the bottom right pixel in the blue channel. So it's really common to make a mistake by switching the XY coordinates because we're used to thinking XY. And so you easily like transpose them, and then you get some weird result or out of bounds. So just one way to correct that would be if you just think of it as rows and columns. Yes?
And the CMOS sensor, is the red and the green like right above each other or next to it? So like in the matrix, would it be next to it or like right above?
So the question in the CMOS sensor, are red and green right next to each other?
Yeah.
Oh, are they like layered? Yeah, so these are all like in the same grid. I mean, so they're all next to each other.
So like their X and Y location like slightly off?
So in this filter, you can think of this as just like a solid sheet that has different colors. I think that's what I think you're asking, like, are these like displaced vertically, right?
No, like if they're like next to each other, even in the matrix, like where you like have like the greens, like extra allocation.
Oh, okay. I see what you're saying. So, okay, so this actually, so originally it will produce a red or green or blue value at each cell or for each pixel. But then the camera will process it to fill in the missing values for red and green and blue. So what the camera will actually give you is a red and green and blue value for every pixel. And it gets that by doing some simple, usually fairly simple process to take the values that it knows and then fill in the values that it doesn't know based on some weighted average of the values that it knows. So you have a dense image, so there's not going to be missing values in the red, green, and blue channels. So we talked about color in terms of physics and perception, but we haven't really talked about color spaces. So you're probably all familiar with the RGB color space, which is the default color space usually. The channels correspond to red, green, and blue. So here I'm visualizing it. This is a color cube, so it's just like the 3D colors. And this is showing the red channel with the other two set to 0, green with the other two set to 0, and blue with the other two set to 0. So this is kind of a default in the sense that our monitors are RGB, our cameras capture in RGB. We have, and part of the reason is that, or the main reason I guess, is that we have RGB cones. But it's actually not very perceptual in the sense that I can't really look at something and say how much red and green and blue is in that color. I think of it as like orange or pink or green or some other like single color, and then maybe some brightness. So it's not perceptual. And also another disadvantage is that the channels are strongly correlated. Like I showed before, if you show these in grayscale, then the red and green and blue values at a particular pixel tend to be very similar to each other, which means that it's an inefficient representation. So that's why it won't be used for like transmission. You'll use YCRCB or another color space because you can more efficiently compress the other signals. So HSV is another one which is designed to be intuitive. So there's hue, which is what we think of as the color, yellow, orange, red, purple. Saturation, which is how bright the color is, going from 0, which would be gray, to 1, which would be like a bright red, or bright whatever color it is. And then value is the intensity. So it's the brightness of the light as a whole. So here the hue is shown with saturation 1, so it's maximum color brightness, and value 1, so it's maximum pixel brightness. And the shadow is blue. Sky is blue, the tree is green, the bricks are red, even the ground is red. Saturation, so here you can see I'm showing the saturation in terms of redder pixels are more saturated. So this is white because it's mostly gray. This is a bit brighter, so the sky is kind of a bright blue, so it's a brighter red there. And then value is the intensity image. So one question is why is the shadow blue? So can you say that a little louder? Right. So so the short answer is that it's because of the sky's color. And so really what's happening is that the building is blocking the direct light from the sun, which is yellow. And it's only the reflection of the sky on this part of the surface is observed. That surface is mostly gray. And so you have a blue light reflecting on the grayish surface, and so the color is bluish. So one thing to note is that this is often used as like a palette or something if you're setting colors in PowerPoint or Word or something. Sometimes it's used for representing colors for like recognition. There's some interesting things like almost everybody's skin color is the same hue It's like a pretty small range of hues, but there's a lot of changes in intensity and saturation. But it can be pretty annoying to work with because the hue is circular. So like 1 and 0 are both red. And so you can't take Euclidean distances between the hues. Also, it comes down to a point. So when value equals 0, then hue and saturation are undefined. Like no matter how you set them, it won't change the RGB color. So it's not like a great space for computing distances between colors. YCbCr is used in like televisions and various things used for transmission. Its advantages are that it's fast to compute and good for compression. So what it is that you separate into like a difference chrominance image, 2 difference chrominance images, and then intensity. So here, Y, the intensity, is basically an average, weighted average of the 3 color channels. CB is a blue minus a red and green, and CR is a red minus a green and blue. And so blue is basically, I mean, CB goes from yellow to blue, and CR goes from green to red. And Y is intensity. And so these tend to be like, here I'm setting CR to 0.5 and intensity to 0.5 fixed, and then just showing CB. Here I'm fixing intensity in CB and showing CR. So the reason why this is important, I mean, why this is more compressible, is that there'll be a lot of changes in the Y channel. So if a signal has a lot of changes, it tends to be harder to compress, especially if the changes are unpredictable. But these tend to be in a pretty small range. They're pretty close to 0. So if you have something where all the values are pretty close to 0, then it's really easy to compress it. You can even just use like zip or something to compress the values. So it basically decorrelates the channels. So now there's not much correlation between CB and CR and between Y. And then another one is the LAB. It's called CIE LAB color space. This was designed to be perceptually uniform. And the way that they did it is that they created like triplets of colors and asked somebody to tune them until like A is as close to B as A is to C. And so by doing that, they could map out some perceptual distance in the color space. And then they created this nonlinear function that maps the colors onto LA and B. It's similar to YCRCB in the sense that you have this A is red versus green, and B is yellow versus blue, and L is intensity. But it's very nonlinear, and it takes a lot longer to compute because the function is much more complicated. But this can be used a bit. This is used fairly often in computer vision as well, when you want to try to represent differences of color or find differences of color. Okay, so we're almost done. We've just got 2 minutes left. Question, which of these do you think contains more information? So I've shown you a bunch of color spaces. A lot of the color spaces have an intensity channel, and they have 2 chrominance channels. So how many people think that the intensity contains more information? How many people think that the chrominance contains more information? So the intensity definitely won by popular vote this time, except for a few people. Sometimes I see the opposite, but I think it depends on who raises their hands first. One good way to see it is that this is and it's correct, that most of the information is in intensity. So if I only look at the color, so I'm making intensity constant and showing all the color, it's pretty hard to interpret. Because there's not a lot of local variation, so it's hard to get much shape from it, and it's more compressible because the values are in a tighter range. So you can represent that information with fewer bits. Where intensity, you get almost all the information from the scene. So there's a lot more information in intensity. So between these 2 images, one might look more attractive, but there's not a big difference in what information you can get from it. Okay, so take-home messages. So the image is a matrix of numbers, light intensities at different orientations, and we can interpret it through local comparisons. We can do those local comparisons and operations using linear filtering, which is a sum of it's the dot product. Sum of dot product is kind of redundant. It's the dot product of the filter with the local image at each position. You need to pay some attention to what size of filter you use and how you crop and stuff like that. And that it's important to be aware of the other color spaces and to use the one that's most appropriate for your application. Thank you. Hi.
I just come back to school yesterday.
Okay.
Can you add me to the wait list now? Because I heard you already sent the wait list to the office. Really, your course is only course at the 500 level.